Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we're going to be looking at topical past paper questions on the topic of medical physics for Cambridge A-level physics. Now, these questions have been put together by myself because we were using Papa Cambridge topical past paper questions, but Papa Cambridge didn't have questions on medical physics and astronomy and cosmology. So I've put together these questions, and I'll leave a link in the description below where you can download these questions, work on them on your own, and then watch this video to help you if you need guidance in the solving of these problems. And in the upcoming videos, I will post and I will share questions on astronomy and cosmology, mostly from more recent exams, and then we can go through those as well. So in the document that I've shared in the description, we are looking at questions 5 to 7 on the topic of medical physics. Again, make sure you try these questions out on your own and are comfortable answering them before you watch this video. Now, this fifth question rather, comes from the March 2023 exam. It's question paper 4, variant 2, and it's question number 9 from that paper. So if you want to, you can go and look and find that exam on your own. Now, we are told to explain how ultrasound waves are detected. So we aren't really cared about the transmission of the ultrasound waves, but we want to know exactly how they're detected. So we know that we need a piezoelectric crystal for the detection of ultrasound waves. We also use the same piezoelectric crystal to transmit the waves, but now we're just talking about the detection. So we can say that a piezoelectric crystal receives the ultrasound waves. And what does the reception of these waves do? Well, it distorts the shape of the crystal. It causes the crystal to vibrate. So you can say any one of those things. So I'm simply going to say it distorts the shape, or its shape, the shape of the crystal, and causes the crystal to vibrate. I'm just going to say causes vibration. So the crystal begins to vibrate. Now, when a piezoelectric crystal vibrates, what do we know? An EMF is induced across its ends. And so the vibrations cause an EMF, and this EMF is something we can detect, we can measure, and we can identify. So we can say that this causes an EMF which can simply be measured. And that EMF is actually a digital signal that we get back, and then we convert it to a signal that we can make an image of and say, well, we can now tell what's happening inside the body. So we only were asked here how ultrasound waves are detected, not how they are transmitted. So these are things that you will read for each one of the techniques that we use for ultrasounds, for X-rays, for PET, and for every type of diagnosis that we are looking at, you should know how they are produced and how they are used for detection, or how they are used for diagnosis, rather. Now, we are told that an alternating voltage V varies with time according to V is equal to V naught sine omega t. The voltage is applied to an ultrasound probe, from the RMS or root mean square voltage is 66 volts. The frequency of the ultrasound generated by the probe is 4.3 megahertz, and we are asked to determine the values of V naught firstly. So V naught, we know the peak voltage. Now this is an AC voltage, or an alternating voltage. It's root 2 times the RMS voltage, root 2 times 66 volts. We are told that the RMS voltage is 66 volts. And so what we get is 93.3, or the two significant figures, 93 volts. So that's the voltage that will provide this ultrasound generation, 93 volts. We're then asked to find the angular frequency of this alternating voltage, and that's omega. Remember, omega is the angular frequency. And we know omega is 2 pi times the frequency. And so this is 2 pi multiplied by, the frequency is 4.3 megahertz, so that's 4.3 million, or 4.3 times 10 to the power 6 hertz. And this gives us an angular frequency of 2.70 times 10 to the power 7. And that will be in radians per second. So again, to two significant figures, this will be 2.7 times 10 to the 7 radians per second. So we now have the peak voltage of the sinusoidal voltage, this alternating current, and we also have the angular frequency. We're then given a table which contains information about air and soft tissue, table 9.1. We're given the density, the speed of ultrasound, and the specific acoustic impedance for air and soft tissue, and we're given the units for each besides the unit for specific acoustic impedance, and that kind of gives us a hint as to what the next question is going to be. Determine the unit for the specific acoustic impedance value shown in table 9.1. So I know that the equation for specific acoustic impedance Z is the density of the medium rho times the speed of sound in the medium C. So if I use square brackets to denote units of measurement, then the units of measurement for Z are the units of measurement for rho multiplied by the units of measurement for C. Now density, we know, is kg per cubic meter. That's kilogram per cubic meter, which is the units of measurement for density, multiplied by the units of measurement for speed, which is meter per second. You don't have to do all of these steps, but they generally do help. And so this is kg per meter squared per second. Since we have a per meter cube multiplied by meter, we get per meter squared. And so I can put this into the dotted line that's under the specific acoustic impedance. So kg per square meter per second. So straightforward, but it's always good to write down the units for each of the things in the calculation to find the overall or the final unit for acoustic impedance. And it's not one that's obvious or easy to remember as well. So it always might be a good idea to just make sure that you have the correct unit. We are then asked to calculate the density of soft tissue. Now the density is not difficult because I used the equation previously, and rho is the specific acoustic impedance of sound in soft tissue, Z over the speed of sound in that medium, so Z over C. And I can take my values from the table, Z being 1.7 times 10 to the power 6. These are all in SI units, and my final answer needs to be in SI units, so that's fine. The speed of sound in soft tissue is 1,600 meters per second, and this gives me 1.06 times 10 to the power 3 kg per cubic meter, the SI units for density. And so, to two significant figures, this is 1.1 times 10 to the power 3, or 1,100 kgs per cubic meter. Now we're then told to use data from table 9.1 to explain why ultrasound cannot be used to produce an image inside an air-filled cavity such as the lungs. Now, why can't we use ultrasound to image inside the lungs? Well, the big difference here that we can see is that the acoustic impedances are very much different. They're not at all equal. There's a very big difference in the acoustic impedances. If we take one and divide it by the other, we have a difference on the order of 10 to the power 3 or 10 to the power 4. So that's a huge difference in the acoustic impedances. And what that means is most of the wave will be reflected. So the wave moving from skin, from tissue into the lungs, most of the wave will be reflected and hardly any will actually go into the lungs. And so we can't actually get our ultrasound in, so we're not going to get anything coming back out. So how do we say this in words? We can do it mathematically as well, but saying it in words is sufficient. There's a significant difference in the acoustic impedance of the two structures, or you can say of soft tissue and air. So what this means is hardly any ultrasound is actually transmitted into the lungs themselves. So almost no ultrasound will be transmitted into the lungs, and that's sufficient wording for the answer. And obviously we require reflections to be able to image inside the body, but if we aren't getting any wave transmitted, there's definitely going to be even less reflected, if anything. And so ultrasounds don't work very well for air-filled cavities for that reason. Since there's a big difference in acoustic impedance, and if you were to calculate the reflection coefficient, you'll see that the reflection coefficient will be almost zero, approximately zero. It'll be a tiny value. So that was a 9-mark question, which focused primarily on ultrasound. There was a little bit of alternating currents, but expect this kind of thing in A-level physics for topics to sort of be mixed together as well. Now the next question is question number 6. This comes from the winter exam of 2022. So winter being November, December 2022. It's question paper 4, variant 2, and it's question number 10 from that paper. We're told that positron emission tomography, or PET scanning, involves the detection of gamma radiation in order to identify the position of origin of positrons in the body. Now, positrons are not naturally present in the body, and we want to explain how positrons come to be present in the body during PET scanning. So our opening statement says there's gamma radiation, but in the question we want to talk about where positrons come from. So PET is positron emission tomography. So obviously there's positrons, but there's also gamma rays. So where do the positrons come from? That's all the question is asking. They aren't asking anything about the scanning itself. They simply want to know where the positrons come from. And the positrons come from a tracer. But they do want us to explain, so saying a tracer is not enough. So what we do is we introduce a tracer into the body. So we can say that a tracer is introduced into the body, and that tracer is radioactive. So we introduce something into your body that is radioactive, and not only is it radioactive, it undergoes beta plus decay. You can draw the symbol for beta plus, it's fine, I'm just going to write it in words. It undergoes beta plus decay. What is a beta plus particle? It is a fast-moving positron. Okay, so it is a positron with high energy. And so when the radioactive tracer is introduced into the body, it immediately undergoes beta plus decay, and that's where the positrons come from. That's all they ask. They only ask where the positrons actually come from. The next part of the question goes one step further and says, explain how positrons cause the emission of gamma radiation from the body during PET scanning. So now we have to go further and talk about where the positrons disappear and the gamma rays appear. So what do we know about positrons? Where positrons are the antiparticles of electrons. Particles and antiparticles tend to not get along very well. And so what happens to the positrons is that the positrons will meet very quickly, actually, will meet, and they'll then annihilate. You can say destroy, that's fine. Annihilate is spelled this way, A-N-N-I-H-I-L-A-T-E. They annihilate electrons in the body after a very short distance. Now, this doesn't tell us anything. So positrons meet and annihilate electrons in the body, but remember Einstein said E is equal to mc squared. We can't simply just lose mass. We have to replace it with the equivalent amount of energy. So the mass of the particles, the positrons and electrons both have mass. So the mass of the particles is, well, we can say, converted into energy, rest mass energy, becoming energy of the gamma ray photons. So energy of gamma radiation. So when the positrons meet the electrons, they annihilate each other and their mass is converted to energy, and that energy is given in the form of gamma radiation. So again, not a very long-winded answer, but it does answer the question. That's how positrons will then cause the emission of gamma radiation from the body during PET scanning. It's then those gamma rays that we actually detect and use to make an image of the body. Part B says, show that the wavelength of the gamma radiation that is detected during PET scanning is approximately 2.4 picometers, and explain your reasoning. So I'm going to draw a bit of a diagram, not completely necessary, but for this explanation I think it is. So I might take a bit longer than you would in answering this question, but I think it will help the explanation. So I have a beta plus particle, which is a positron. I can say E plus, that's fine. And I have another particle with the same mass, which is an electron. And I need to find the wavelength of the gamma radiation. So I have to do a little bit of particle physics here to get this final result. When they meet, they collide, they destroy each other. And now we don't need to explain why, but we do need to include it in our calculation. Instead of one gamma ray being produced, 2 gamma rays are produced, and they they move in opposite directions. They move in 180 degrees from each other, and this is to conserve momentum. But that's a different question altogether. So in my explanation, because they did say explain your reasoning, and I can see this is a 4-mark question, I can say that the annihilation produces 2 gamma rays. And you can go back to your topic or go to the crash course that I posted on this topic to ensure that you understand why 2 gamma rays are produced rather than 1 when the beta particle and electron, or rather the positron and electron, annihilate each other. But basically what I can see is that 2mc squared, where m is the mass of the positron and electron, which is the same, is equal to 2 times the energy of a gamma ray photon. So each of these gamma ray photons have the same energy, hc over lambda. Obviously the 2's disappear. I'm left with the wavelength of one of these gamma rays, lambda, is Planck's constant h divided by the mass of a positron or electron multiplied by c. Now if I put my values into this equation, this is 6.63 times 10 to the minus 34 joule seconds divided by, now don't be confused by this mass, this is the mass of an electron, of a positron. It's 9.11 times 10 to the minus 31 kg, and the speed of the electromagnetic wave is 3 times 10 to the power 8. And so if I calculate this, I get what the question required of us, 2.4 times 10 to the minus 12 meters, which we know to be 2.4 picometers. So pico is 10 to the minus 12. And so this is how you would find the wavelength of gamma radiation. You always say that there are 2 particles destroying themselves to give us 2 photons. And that way you get mc squared equal to hc over lambda, and you can find the wavelength lambda of the gamma rays that are produced. So 2.4 picometers, and that's the thing that we need to detect. That was the long question that was really mathematical for 4 marks, but it wasn't very long if you didn't draw the diagram like I did. You could simply say annihilation produces 2 gamma rays and then go straight into the equation, which means you could do this in a fairly short space of time. But it does mean that you need to understand your theory on this topic very well. So another 9-mark question. Not difficult, but does require you to understand your concepts. And you can see applications of different parts of physics from AS to A-level all coming together in this topic, as they do for most A-level topics. Next question is from the summer exam of 2022, that's May-June 2022. It's question paper 4, variant 1, and question number 9 from that paper. And right off the bat, we are asked to explain how X-rays are produced for use in medical diagnosis. So maybe a good thing to do with answering these questions is to just underline the key words here. Explain how X-rays are produced. So specifically produced, but specifically produced for use in medical diagnosis. That means how are they produced, as your textbook said they were produced. Okay, so X-rays specifically for medical diagnosis. We don't want to know how they are detected, we simply want to know how they are produced. So how do we produce an X-ray? Well, we apply a potential difference. I'm going to say PD because I'm lazy, but you shouldn't be as lazy as I am. An applied PD accelerates electrons toward a metal target. You don't really have to specifically talk about cathode and anode. A metal target is perfectly fine. So an applied potential difference accelerates electrons toward a metal target. And what do the electrons do? The electrons decelerate upon the collisions that they undergo with the metal target. So I'm going to say upon collisions with the metal atoms. And we know that when electrons are decelerated, because they lose energy, they give off that energy in the form of radiation. So the electrons decelerate upon collisions with the metal atoms, and the loss in electron energy is the energy of the X-rays that are produced. And remember, the loss in electron energy differs from electron to electron, so the energy of the X-rays produced also differs from X-ray to X-ray. So when we apply a potential difference across a anode and cathode, and this accelerates the electrons toward the metal target, the electrons will decelerate when they strike the metal atoms, and the loss in electron energy is the energy of the X-rays that are produced. So if we have a high enough potential difference, then we ensure that X-rays are produced and no other types of waves. Next, we are told to state why X-ray images are taken of multiple sections of the body during computed tomography or CT scanning, also known as CAT scanning, CAT. So why is it that we use multiple sections of the body when we're doing CT scanning? So a CT scan is basically just a compilation of X-ray images. So what we do is we take images of multiple sections and then we combine them. So images of multiple sections of the body, simply say images of multiple sections, are combined. Why would we do that? Why would I take multiple X-rays rather than just a single X-ray? Well, we do this in order to create a three-dimensional image. And if you wanted to, you could add that this allows information about the depth of certain anomalies in the body to be imaged. So that's the reason why we create a 3D image, so that going one step further. But basically, we take multiple images of multiple sections to create a three-dimensional image. Once we have the depth, we have much more knowledge about the thing that we are studying, and so we can go into detail trying to understand how deep inside the body an anomaly or some abnormality is. Part B says an X-ray image is taken of the structure shown in the figure. We're shown soft tissue, bone, and soft tissue again on the other side. We have incident X-rays on the left and detected X-rays on the right. And we're given the distances, the lengths. The soft tissue covers 5.6 centimeters, and right in the center we have the bone covering 2.4 centimeters. We're told that the linear attenuation coefficient of bone is 3.4 per centimeter, and the linear attenuation coefficient of soft tissue is 0.89 per centimeter. The incident X-rays are parallel and have a uniform intensity I naught across the structure. And so you probably know where this is going. We are told now to determine in terms of I naught the intensity of the detected X-rays from the point P. So where's the point P? Okay, so the point P, the X-rays go into the soft tissue and then out on the other side. And we're given the linear attenuation coefficient of soft tissue to be 0.89 per centimeter. So it's not passing through bone in this part of the image. So what I get is that the transmitted intensity I is equal to I naught e to the minus mu x, and I'm going to put subscript tissue because the mu value, which is the attenuation coefficient, is that for tissue, and x is the distance that the X-ray traveled through tissue. And so this is E. Now they want it in terms of I naught, since we don't actually have a value of I naught, so it's just going to be a fraction of I naught. So that's e to the minus 0.89. I can leave my values in centimeters because I'm multiplying per centimeter times centimeter. It's minus 0.89 times 5.6, and all of this multiplied by I naught. And so when I compute this, I get this to be 6.84 times 10 to the minus 3 I naught. And so to two significant figures, this is 6.8 times 10 to the minus 3 I naught. So I still have some intensity on the other side. It might be lower, but there's still some intensity of the X-rays detected on the other side of the soft tissue. Now point Q is a little bit more difficult, because point Q, the X-ray passes into the soft tissue and then through bone and then through more soft tissue. So essentially I'm going to have to calculate the distance it travels through tissue and then the distance it travels through bone. But how do I calculate what the final intensity is going to be? Now you don't need to do this that I'm going to do next, but I think this might help. Just might help the understanding. Bear with me, this might take some time, but I have an incident intensity I naught going into tissue. I'm going to exaggerate this diagram slightly, and I'm going to redraw the bone, and I'm going to assume that soft tissue obviously has a linear attenuation coefficient mu. I'm going to call it mu1, and then bone has a linear attenuation coefficient mu2. So I'm going to assume that after traveling a distance x1 through soft tissue, the incident intensity onto the bone is I1. The X-ray then travels a distance x2 through the bone and then exits with intensity I3. It then travels another distance through the remainder of the tissue x3, and then the intensity, actually I'll call this I2 since we're going in order. So I0, I1, I2 exits the bone, and I3 finally exits on the outside. So I have tissue, bone, and tissue. And we're going to see if the order through which the X-rays passes through these structures actually makes a difference. So this is going to be a little bit mathematical, but if I wanted I1 would be I0, what goes into the soft tissue, I0 e to the minus mu1 x1, and then I2 would be the incident intensity for the bone would be I1, what's going into the bone, e to the minus mu2 x2, and I can write I1 in terms of what I have above, so it's I0 e to the minus mu1 x1 times e to the minus mu2 x2. And then what I actually want is what's the intensity on the other side at point Q as it's labeled in the diagram, I3. And so this is going to be I2 e to the minus, and we're looking at the coefficient of soft tissue, which is mu1, times the distance it travels, x3. We aren't sure if it's actually symmetrical, if x1 and x3 are the same, so we're just going to label them differently. And what this is I2, which is I0 e to the minus mu1 x1 e to the minus mu2 x2 times e to the minus mu1 x3. And if I do a little bit of mathematics, I can see that this becomes I0, the initial incident intensity, e to the minus, now I can group whatever has a mu1 in the coefficient, so e to the minus mu1 into x1 plus x3, so I can actually add the distances together, and I can multiply it by e to the minus mu2 x2. Aha, so this is actually very simple. Now, you may have very good mathematical skills and you could identify this immediately, but if you don't, this is the reason we say the final intensity is e to the minus mu, which is the attenuation coefficient for one of the media, times the distance it travels through that media. So in this case, that's tissue, the total distance to the tissue, irrespective of the order, multiplied by e to the minus mu x for bone. And so this would be the final intensity I3. And so you may see this in the mark scheme, but not sure how we get that. So this was a little bit of extra mathematics, which you don't need to do, but you could do it to prove to yourself this is why the mark scheme takes the initial intensity and multiplies it by the product of the exponential terms for each of the structures. And so I can simply say I is I0 e to the minus mu x for bone, where x is the total distance traveled in bone, e to the minus mu x for tissue, the total distance traveled in the soft tissue. And now I can just put my values in. So this is e to the minus, and again I can leave everything in centimeters, minus 3.4 times 2.4 multiplied by e to the minus 0.89 times 3.2, all multiplied by I0. So if I compute this, I get 1.66 times 10 to the minus 5 I0. It's a tiny amount that actually passes through. So it's 1.7 times 10 to the minus 5 I0, and that's in two significant figures. And so that's the detected intensity after passing through bone and tissue. So you can see that all the mathematics that I did down below can be simplified into one very simple expression. So whenever you see X-rays passing through multiple media, you can just remember that this is the expression of the intensity after it has passed through all of those different media. Now, the last question says, explain with reference to your answers in B whether the X-ray image of the structure in figure 9.1 has a good contrast. Now, there isn't really a correct answer here because we don't really know what a good contrast would be, but we should make some comparison of the detected intensities when the X-ray passes purely through soft tissue and when it passes through soft tissue and bone. So what I'm going to do is I'm going to look at the orders of magnitude, the 10 to the minus 5 and the 10 to the minus 3, not so much the values, but we can if we wanted to. So if I take 10 to the minus 3, which is the order of magnitude of the intensity when it passes purely through soft tissue, and I divide it by 10 to the minus 5, what I get is there's approximately a difference of 10 to the power 2. So there's 100 times the difference in intensity. So I have to make a judgment based on these values, and what I'm going to say is that the detected intensities, I'm going to say that the detected intensities differ by a significant amount. So detected intensities differ by a factor of approximately 100. So what this means is that there's a big difference in intensity for what goes through tissue and what goes through bone. So I'm going to say, yeah, I think there is a good contrast. So what you really need to do here is make some comparison of the values. So comparison of the orders of magnitude. If you made some errors in the calculation for P or Q and you find that your intensities are slightly closer, then you can say the detected intensities differ by a factor of whatever, maybe 2, and so that's not enough, and so the contrast isn't good. But I would think that 100 times more intense would be a significant difference in intensities, and hence a significant difference in the darkening of the image, which is what contrast tells us, and so that should be good enough contrast to tell that I'm looking at bone rather than soft tissue. And that was another 9-mark question, and was a little bit of mathematics involved. But once you are happy with why I used the equation I did in question B2, then you can use it as is going forward. I think it's important because sometimes we're looking at mark schemes and we don't really know where equations come from, but that was hopefully quite helpful. And so these are all the questions that I put together for medical physics. I hope these were helpful. The question structure may change slightly from paper to paper, but what you'll notice is that the core remains the same. Do you understand ultrasound? Do you understand X-rays? Do you understand PET scans and so on? And do you understand basically how they're produced and how they're used for imaging? And then there are slight nuances in each of these sections that you have to understand and get. And the linear attenuation coefficient works for ultrasound just as it does for X-rays. It's only that we're talking about 2 different types of waves, but the equation looks the same. And so there is a bit of reading, but with some application, things get better. So I hope this video was helpful. If it was, please leave a like, comment down below, subscribe to the channel if you haven't already. The next video, I will put together some questions on astronomy and cosmology, and then maybe we'll move on to paper 5 afterwards. But from me, Mr. K, that's all for now, and I'll see you again next time on Everything is Relative.